So let's get back to irodov. Okay. So look at this question. Okay. In this question, a ball falls down. Okay. And we have to find out the difference in angular momentum. That means final angular momentum minus initial angular momentum. Okay. So pause and just read the question now. Just pause it and read it once. Okay. So see, what's happening in the question is a ball of mass m, okay, kept at height h. Okay. And this ball, okay, will fall down. Okay. Initial velocity of the ball was 0. Final velocity of the ball would be under root of 2gh. Fair and fine. So you have to find out the difference in angular momentum. That means angular momentum when the ball is out here. That means final angular momentum. That means angular momentum when the ball reached out here. Okay. Final angular momentum minus initial angular momentum. Fair and fine. There's a little bit of twist in the question. The twist out here is we have to find this angular momentum, a difference in angular momentum from the frame of reference of a body that is moving with velocity v. That means from the frame of an observer that is moving with velocity v. With respect to him, okay, what is the final angular momentum minus initial angular momentum? So this is the question. Okay. So if we make the observer static, okay, suppose I'm drawing a line out here, and out here I'm making my observer static. Okay. If my observer is static, how will he see the initial ball? How will he see this ball? He'll see this ball moving with velocity v towards left, isn't it? The velocity of the frame would be added to the velocity of the ball. Okay. And finally, okay, or what will be the path of the ball? See, with respect to this observer, okay, the ball was initially out here. Okay, there was initial velocity in this direction, which is equals to v. There is acceleration of gravity in this direction, which is g. And the initial velocity in downward direction is g, isn't it? So initial velocity in downward direction is 0, isn't it? Because the ball was dropped from out here. So the ball will follow a trajectory in this manner. Understood? And the ball will come out here. And this path is with respect to the observer out here. Okay? And the ball will straightly come down with respect to someone sitting on the ground. This is the trajectory as observed by someone sitting on the ground. Okay? This is the trajectory as observed by this frame of reference or this observer. Fair and fine. Now you have to find out angular momentum. Okay? What was the formula for angular momentum? Check. What is the formula for angular momentum? This is, see, angular momentum was nothing but how much? L is equals to what? Angular momentum is equals to r cross p. P is nothing but linear momentum, mass into velocity. Okay, we take out the mass common. Angular momentum is equals to mass into r cross v, isn't it? So angular momentum out here is equals to mass into r cross v. Okay, angular momentum vector is equals to mass into r cross v. Out here, mass is the mass of the object, fair and fine. R is the position vector of the object. Now to calculate the position vector of an object, we need an origin. Okay, and what is the origin out here? See, the origin out here is nothing but the observer. Okay, see, if you look initially, the observer was out here. Okay, let's delete this observer. Let's erase this observer. If you look initially, the observer was out here. Okay, the observer was out here, and the ball dropped like this. Okay, finally the observer will be at same place because the observer is not moving with respect to himself. No. Okay, and the ball followed this trajectory, isn't it? So the position of observer will be treated as the origin. Understood? Initially, the r vector is nothing but the height vector. Okay, and finally, the r vector is nothing but the distance or horizontal distance from the observer. Initially, this is the r vector. Finally, this is the r vector. Okay, this is the final or r initial vector, r final vector. Okay, you have to find out angular momentum final minus angular momentum initial. No? So change in angular momentum is equals to final angular momentum minus initial angular momentum. All of them are vector quantities. This much is understood. Okay. So we start with initial angular momentum. Initial angular momentum is nothing but m into r cross v, where r is nothing but height and v is nothing but the initial velocity v in this direction. Okay. R cross v is nothing but magnitude of r into magnitude of v into sine of angle between r and v. What is angle between r and v? 90. So initial angular momentum is nothing but m r into v. Okay. Just wait a minute, my pen is in writing. M r into mr into v, and sine of 90 is nothing but 1. What is the final angular momentum? Acha, the direction of initial angular momentum is nothing but r cross v. That means it is towards v. You always use your right hand. See, this video is mirrored kind of thing, so you might have some confusion. But while using cross product, always use your right hand. Okay, r cross v. That means the angular momentum is towards v. Okay, final angular momentum. To find out the final angular momentum, we need to find out the final velocity or linear velocity or final linear velocity. What is the final linear velocity out here? See, this component of velocity would remain unchanged. Okay, and there would be downward component of velocity. Why? Because the ball is also being accelerated by gravitational forces, no? Or gravitational acceleration. Okay, so if I apply v square is equals to u square plus 2gs or as, where a is nothing but acceleration due to gravity, s is nothing but the height dropped, initial velocity is nothing but 0, we'll get final component of downward velocity is equals to under root of 2gh, isn't it? So final component of downward velocity is equals to under root of 2gh. Okay, and the total velocity of this particle at this position is a combination of this velocity plus this velocity. That means the vector summation of this velocity and this velocity. Or magnitude is nothing but v square plus 2gh under root. Okay, x square plus y square under root. Understood? Okay. Now while applying, see, let's suppose this is the total velocity vector. This total velocity vector is a combination of this vector and this vector. That means the vector summation of this vector and this vector. Okay. Now my angular momentum is nothing but mass, which will remain as it is, into r final. Okay, let's write down r final. Okay, into magnitude of r final into v final or v total into v total. Okay, into sine of angle between v total and this one. Okay, v total and r final into sine of theta. Sine of theta, and I have already explained it. Okay, Vt sine theta is nothing but under root of 2gh. Okay, see, Vt sine theta. Sine theta is nothing but this angle plus entire this angle. Okay, that means what? We have to take a component of this Vt force along this line or along the vertical line. So Vt sine theta is nothing but under root of 2gh. I have already explained this in previous video. Just go and check it out. Okay, so Vt sine theta is nothing but under root of 2gh. 2gh. My pen is not functioning. I don't know why. Under root of 2gh. Okay. Okay. Now problem is, what is r final or what is this much distance? What is this much distance? If you look carefully, okay, the initial component of velocity in this horizontal direction is v. Is there any acceleration due to gravity in this direction? No. So distance traveled, okay, is nothing but v into t. But t is nothing but time taken to drop. That means the time taken to for the ball to come out from head to out head is equals to time taken by the ball from out head to out head, isn't it? So let the time taken to fall down is equals to t. Okay, let the time taken to fall down is equals to t. Time taken to fall down. Okay, RF or vertical component of distance. So not vertical, horizontal. RF is equals to S is equals to ut plus half at square, isn't it? The initial or the horizontal component of acceleration is equals to 0. So this entire term would become 0. Okay. If u is 0, sorry, if u is out here, if this u is nothing but the initial velocity v. So if u is initial velocity v, final RF or this RF is nothing but v into t, isn't it? This RF is nothing but v into t. Okay. Now what is the time t? Can I say the time taken to fall down? Okay. How do I find out? By taking the vertical component. If I take v is equals to u plus at, this is the vertical component of equation. Okay, v is equals to u plus at. When I'm writing it, this is nothing but the vertical component of equation. Okay, so v is nothing but the final velocity out here, or final downward component of velocity, nothing but under root of 2gh. Under root of 2gh. Initial vertical component of velocity is equals to 0. Acceleration due to gravity is nothing but g. So we get under root 2gh, under root of 2gh is equals to how much? G into t. Or if I calculate this from here, this t is equals to under root of 2h by g. Under root of 2h by g is equals to t. Okay, can I substitute this t out here? Okay, if I substitute this t by this t out here, what do I get? Final position vector is nothing but v into t, where t is nothing but under root of 2h by g. Okay, so our final is nothing but v into under root of 2h by g. Okay, 2h by g. Okay, g and g out here would get cancelled. If I multiply them, g and g out here would get cancelled. Under root of 2h and under root of 2h would become 2h. Okay, our final angular momentum is equals to mvh, or 2 mvh, 2 mvh. Okay, 2 mvh. Okay, initial angular momentum is equals to m into r initial into v, but r initial was already h, isn't it? R initial was already h. Okay, so change in angular momentum. Change in angular momentum is nothing but final angular momentum minus initial angular momentum, or 2 mvh minus mvh, which is equals to mvh. And this is how we solve this question 189. Okay. Now there is one more way of solving the question. Okay. As I said, rotational mechanics is equivalent to linear mechanics, isn't it? So in linear mechanics, if force is equals to rate of change of momentum, okay, can I say in rotational mechanics, torque is equals to rate of change of angular momentum, isn't it? Whatever is equivalent of force in linear mechanics, that is the equivalent of torque in angular mechanics. Okay, momentum, linear momentum, this is angular momentum. What was the relation between torque and force? The relation between torque and force is given by torque is equals to r cross f, isn't it? Or r is the position vector from which the force is applied, or point of application of force, isn't it? Fair and fine. Now see, from the observer, or from the perspective of observer, okay, the ball is out here and the ball will follow this trajectory. Okay, the ball is out here, the ball will follow this trajectory. Fair and fine. Now what is the r vector? If you see properly, the r vector keeps on changing. Initially the r vector was out here. Okay, initially this is the r vector. After some time when the ball is out here, the r vector would be somewhat like this. After that, when the ball is out here, okay, the r vector would be somewhat like this. When the ball reaches out here, the r vector would be this much. When the ball is at in position, the r vector would be this much. So the r vector, or the direction of r vector, keeps on changing. Okay, the direction of force vector. What is the force acting on this mass? The only force acting on this mass is mg, isn't it? So if I say mg is acting downward, okay, now tell me what is r cross h. Okay, so previously I taught you, if you draw a line, okay, perpendicular to mg, because mg is always in downward direction, no? So if you draw a line perpendicular to mg, okay, let's draw a line perpendicular to mg, okay, and let's say this line is shifted out here, okay, and take component of all the values of r, okay, along this perpendicular, or this line, the line that is drawn perpendicular to mg, will get r cross f, isn't it? So let this horizontal line be dragged out here. Okay, that means this horizontal line, or the line that is perpendicular to mg, is drawn out here. And what you have to do is you have to draw all the components of r along this line. Okay, so let's say after some time the r will be, value of r would be this much. After some time the component of value of r would be this much. After some time the component of r perpendicular to mg would be this much, and finally the component of r perpendicular to mg would be this much. So you see, the value of r, or component of value of r, keeps on changing. Therefore the value of torque also keeps on changing. That means what? Somehow I get the intuition that we have to do some kind of integration. Okay, so let's say from this equation, torque is equals to dl by dt, I can say that torque into dt is equals to dl. Torque dot dt is equals to dl. But torque into dt is nothing but changing angular momentum. Okay, what we have to do, we have to take the component of r along this horizontal line. Okay, so if you check out here, suppose the ball brought for some distance, that means the ball went out here for time t dash. Okay, the perpendicular component will be vt, isn't it? vt1 at time 2 when the ball is out here. The component of, or perpendicular component of this component would be nothing but v into t2, where v is nothing but the horizontal velocity of the ball as seen by this observer. So I have to integrate all these perpendicular components or all these horizontal components of r along this line. So out here, the horizontal component is Vt1, out here the horizontal component is Vt2, out here the horizontal component is Vt3. So can I say torque is nothing but R into F? R is nothing but V into T. Okay, T is nothing but the time at which the ball is seen. Okay, if the ball is seen out here, Vt is this much. If the ball is out here, Vt is this much. One thing you have to understand is out here T is variable. That means torque or the magnitude of torque is also variable. That's why you are doing the integration. Okay, so what is the value of R? Vt. What is the value of F? Mg. And Mg is constant. Okay, now if I take torque is equals to Vt into Mg. Okay, Vt cross Mg. This is the value of torque. Okay, the time is variable out here. That means the time depends on which position you are seeing the particle at. Okay, if you see the particle out here, the Vt is nothing but this much. Okay, understood this much. Now if I use this equation, okay, torque is nothing but Vt mg into dt is equals to dl. If I integrate this much, okay, v, m and g are constant. T dot dt is equals to integration of dl, or vmg integration of t dt is nothing but t square by 2, isn't it? T square by 2, okay, is equals to change in angular momentum, final angular momentum minus initial angular momentum. Fair and fine. Okay, or L, or I can write this as L. Okay, now out here, what are the lower limits and upper limits? Okay, and out here, what are the lower limits and upper limits? At the position of it, the lower limits of is initial angular momentum, the upper limit is final angular momentum. So final angular momentum minus initial angular momentum is nothing but del L. Okay, we use that notation. See properly out here, t square by 2. Initial, what is the initial value of time? 0, because the ball started when the ball started out here. The initial time was equals to 0, no? What is the final time when the ball reached out here? The final time when the ball reached out here is nothing but, see this one, what is it? Under root of, what is the final time? What is the right time? Under root of 2h by g. See this section, okay? This section, under root of 2h by g. So the final time is nothing but under root of 2h by g. But h is nothing but the height at which the ball is kept. So now if I integrate this, vmg is equals to t square by 2 minus 0 square by 2, or 2h by g is nothing but t square divided by 2 minus 0 is nothing but final angular momentum minus initial angular momentum. Okay, this is the equation that I wrote out here. Okay, what do I get? You can cancel out the 2. Okay, and I can, okay, so out here I would get nothing but vmg h by g minus 0 is equals to final angular momentum minus initial angular momentum is nothing but change in angular momentum that is asked in the question. If I cancel out the g and g, I'll get vmg is nothing but change in angular momentum. vmh, sorry, vmh. So if I erase this and write vmh is equals to change in angular momentum, this is the answer that we get. And this answer is same as the previous answer that we got. See, in the previous question, what is the answer that we got? The answer that we got is out here nothing but mvh. See out here, this was the final answer, no? Okay, mvh. And out here, look, the final answer is nothing but mvh. Okay, so you can do this by 2 methods, whichever you like. Okay. So in this question, just pause and read the question properly. Okay, just pause once and read the question. Okay. So in this question, what is being said is that there is a circular disk that is rotating with angular velocity omega. Okay, just for the sake, what is the direction of angular velocity omega vector? If I use my right hand, see, some of you might have confusion that you are using the wrong hand. It's not like that. The screen is mirrored. Okay, so having said that, if I use my right hand and curl my finger or curl my right hand in the direction of angular velocity, the thumb is the direction of angular velocity vector, isn't it? So the angular velocity vector is coming in this direction. Fair and fine. So this is the direction of angular velocity omega. Okay. Now what the question is saying is that the disk is rotating in this direction. Okay. Now an observer is out at the disk, or observer is at the center of the disk. Okay. And this observer throws another disk of mass m with velocity v naught. Okay. At time t is equals to 0, this observer sitting on the disk that is rotating with angular velocity omega throws a particle of mass m with velocity v naught. Fair and fine. And this v naught is with respect to the observer. That means the velocity v naught is observed by the observer himself. Okay. The question is asking, find out the angular momentum of this mass as a function of time with respect to this observer due to Coriolis forces. Okay. So what did I say? Every rotating frame has two pseudo forces. First one is the centrifugal force. Second one is the Coriolis force. So in this question, the effect of centrifugal force is not taken into account, okay, or not considered out here. We have to find out the angular momentum of this particle, assuming only Coriolis force is acting on this particle. Okay, okay. So in the lecture of dynamics, what did I say Coriolis forces was? If Coriolis was nothing but minus 2m omega cross v, isn't it? If I want to multiply the minus inside the bracket, it would be v cross omega. Okay, if you multiply cross product with minus, it just changes the direction. So instead of omega cross v, I'll write v cross omega. Well, m is nothing but the mass of the particle, isn't it? V is nothing but the velocity of the object as seen by the rotating observer, and omega is nothing but the rotational angular velocity of the observer himself. So out here, v out here becomes nothing but v naught. Okay. Now see, if I draw the free body diagram, okay, this is velocity vector v naught. Just tell me which direction is the Coriolis force acting. See, if I use my right hand, okay, v naught cross omega, that means Coriolis force is acting downward, no? So this is the direction of Coriolis force, or force is equals to 2mv into omega. 2mv into omega. Fair and fine. But sir, you have found out Coriolis force, that is fair and fine. Okay, you have neglected centrifugal force, even that is fair and fine. But how do I find out angular momentum of this particle that is moving away with velocity v naught with respect to this observer? Or how do I find out the angular momentum? See, so somehow I know angular momentum is related to torque from the previous question. Just recall, force is equals to dp by dt. Therefore, torque is equals to dl by dt. So we know that torque is equals to rate of change of angular momentum from the equivalence of linear mechanics, isn't it? And the relation between torque and force is nothing but torque is equals to r cross f. See, if we just recall the formulas, torque is equals to r cross f, isn't it? So out here the value of torque would be nothing but torque is nothing but r cross f, where r is the position vector. Okay, now see, our observer is sitting at the center of the disk, and this block is, or this mass m is moving away with velocity v naught, as seen by this observer. Okay, the Coriolis force is acting in downward direction, which is given by 2m v into omega, or v naught into omega. V naught is the velocity of the object as seen by the observer. Fair and fine. Now, after certain time, what is the value of r? Okay, my question is, what is the value of r? So to find out the value of r, we must use a variable of time. Why? Because initially the particle was at near the disk, or the distance between the particle and the disk was 0. But as the time goes on, the particle will go further and further away from the disk. No, the particle will also move in downward direction because due to this force. But the particle, this component of velocity would not be changing, isn't it? Okay. So this particle is moving away and away from the disk. Okay. Now see, after certain time, what will happen? After certain time, the particle reached out here, that is moving with velocity v naught. Now my question is, what is this much distance? Okay, what is this much distance, or this much distance? Okay, this much distance is nothing but v naught into t. Suppose at time t is equals to 0, the particle has started out here. At time t is equals to t, this much distance is nothing but v naught into t. No, distance is equals to speed into time. So this much distance would be nothing but v naught into t. V naught into t. Okay, so this much distance became v naught into t. Fair and fine. I found out this much distance v naught into t because I need the value of r. This value of r is nothing but this much distance, or the position vector of the particle. Okay, so this is nothing but v naught into t, and the force acting on the particle was nothing but 2m v naught omega. Force acting on the particle was nothing but 2m v naught into omega. Okay, now see, one thing you have to see out here is the torque out here. Okay, the torque out here is variable. Variable means what? See, as the distance is increasing, okay, as the distance is increasing, the force will remain same as it is, no, isn't it? So r is increasing. Therefore, if r increases, the torque also increases, no. So somehow, if you have to write the angular momentum as a function of time, you have to integrate this one, isn't it? So if I write my entire equation, now just see this equation. Okay, if I just write this equation as v naught t into 2m v naught omega is equals to dl by dt. Okay, dl is the angular momentum and dt is the time. Out here v naught and v naught will become v naught square. So this v naught and v naught will become v naught square. And if I send this dt to the left hand side, it will become 2m v naught square omega into t dt is equals to dl. Now if I integrate the entire thing, see, if I integrate left hand side and right hand side, this 2m v naught square omega is already a constant. None of them are changing, isn't it? Now this t dt with respect to dl, okay, dl is nothing but change of angular momentum, okay. Initially, when the particle was near the origin, the torque was equals to 0. That means r is equals to 0. So whatever is the Coriolis force doesn't matter. The torque was equals to 0. Okay. So when torque was equals to 0, the angular momentum of the particle was equals to 0. You can even say that angular momentum is equals to r cross linear momentum. So even if the body had some linear momentum, the value of r was 0. So initially the value of angular momentum was equals to 0. Why? Because angular momentum is equals to r cross linear momentum, isn't it? And linear momentum was some finite value, but the value of r was 0 initially. Okay. So the value of initial angular momentum is 0. But to find out the value of final angular momentum as a function of time, isn't it? So let the angular momentum be L. See, irodov out here is using the notation of N, but I'll be using L. Okay, it's better if you use the notation that is used in GEE syllabus. And from time t is equals to 0 to time t is equals to t. So if I integrate this one, it will become 2m v naught square omega t square by 2 is equals to L. See, I integrated this function out here. Okay. Now 2 and 2 will get cancelled. So our value of angular momentum is nothing but m v naught square omega t square is equals to angular momentum as a function of time. So this is our answer. Understood? Just pause and look at this question. Okay. So in this question, okay, I just simplify the question for you. In this question, a body is moving in an elliptical orbit. Okay. Suppose this is Earth, this is Sun. Suppose Earth is moving around Sun in an elliptical orbit. Okay. Mind you, this is not the chapter of gravitation. That means the force that is being talked out here is not about gravitation. Okay. But the forces that I'm explaining out here, or the elliptical orbit I'm explaining out here, will follow similar mechanics same as gravitation. Okay. What I'm trying to say is the forces acting on Earth are central forces. Central forces means what? Central forces means forces acting throughout the point. That means at every part of the ellipse, okay, the forces will be directed towards the sun. Okay, the force out here would be towards the sun, the force out here would be towards the sun. Just imagine gravitational forces. For a moment, just imagine that forces that is being talked out here is gravitational forces. Okay, so out here, the direction of force would be towards the sun. When the earth is out here, the direction of force would be towards the sun. When the earth is out here, the direction of force would be towards the sun. So when this kind of forces act, that means all the forces are directed towards a point. These kind of forces are called central forces. And we have done in previous lectures, just follow work energy theorem lecture 5 or 6. Out there I have already said the central forces are always conservative in nature, isn't it? So even this force is conservative in nature. Okay. And one more thing. Suppose when the earth is out here, what is the direction of force? This one. Okay. When the earth is out here, what is the direction of force? Towards the sun. Now just for a moment, let our observer be at sun. Okay. If my question is, what is the torque acting on Earth as observed from Sun? See, what is the formula for torque? Torque is equals to R cross F, where R is the position vector and force is nothing but the force of interaction or force acting on the particle. Now, when the Earth is out here, what is the direction of R? The direction of R is nothing but a straight line connecting these two parts, isn't it? Our observer is at the Sun. Okay, so a straight line connecting these two parts, and the force is also along the same straight line. When the Earth is out here, R, the value of R is nothing but this one, and the direction of force is also along the line. So the angle made by R and F is always 0 throughout the elliptical orbit. So if the angle made between R and F is always 0, that means what? The torque acting on this Earth as observed from the Sun is always 0, isn't it? That means magnitude of R into magnitude of F into sine theta. The theta is the angle between R and F. So sine theta is always 0. So if sine theta is always 0, the torque acting on Earth as observed from Sun is always 0. So if torque acting on the Earth is always 0, can I say the angular momentum will never change? Why? Because force is equals to dp by dt. Similarly, torque is equals to rate of change of angular momentum. So if torque is 0, the angular momentum never changes. So the first thing in elliptical orbit, we learn that if central forces are acting, okay, that means the direction between or the angle between R and F is 0. If central forces are acting, that means the torque is equals to 0. So if torque is equals to 0, angular momentum in an elliptical orbit is always constant. Okay, angular momentum is conserved. The second thing that I said is central forces, okay, are conservative in nature. That means what? See, if all the forces acting on Earth are conservative in nature, then we can apply conservation of mechanical energy. That means if all the forces acting on Earth are conservative in nature, kinetic energy plus potential energy will always remain constant. That means kinetic energy plus potential energy out here is equals to kinetic energy plus potential energy out here is equals to kinetic energy plus potential energy out here is equals to kinetic energy plus potential energy out here. That means if all the forces acting on the particle are conservative in nature, kinetic energy plus potential energy is always conserved. Okay, so kinetic energy plus potential energy is constant. So this, using these two principles, I'll solve this question. Now in this question, what is saying is that a central force is acting on this particle. Okay, when the particle is at nearest distance, that means out here. When the particle is out here, okay, this distance is given by r1. Okay, the velocity of Earth is v1, isn't it? And when the Earth moved from out here to out here, okay, it went to the elliptical orbit and came out here. So when the Earth reached at value of r2, or at the farthest distance, the value of velocity of Earth is nothing but v2. Okay, now what the question is asking is that using the value of r1 v1, okay, r2 and v2, I have to find out the mass of the Earth. Fair and fine. So first thing I'll do is conserve the angular momentum. So what was angular momentum? Angular momentum is equal to nothing but m into r cross v, isn't it? So angular momentum throughout the elliptical orbit is same. Why? Because no torque is acting on the Earth as observed from the sun. So if I calculate the angular momentum out here, what is angular momentum? M into r1 into v1, because r1 is perpendicular to v1. So angular momentum at nearest distance is equal to m r1 v1. What is the angular momentum at farthest distance? M into r2 into v2. Out here, even at the farthest distance, r2 is perpendicular to v2. So is equals to m into r2 into v2. What I did out here is m r1 and v1 is nothing but the angular momentum of Earth out here. M r2 v2 is nothing but the angular momentum of Earth out here. And all I'm saying is that angular momentum of the body of Earth out here would be same as angular momentum of the Earth out here. And angular momentum of the Earth throughout the entire orbit would be same. That is all I'm saying out. Okay. So this is our first equation. Now if I just take these two parameters, okay, just these two parameters, can I say r1 v1 is equals to r2 v2? Just take these two parameters and cancel out them, isn't it? So this is my first equation. And the second equation that I'm using is kinetic energy plus potential energy is equal to constant throughout the orbit. Okay. So what is the kinetic energy out here? Half m v1 square. Half m v1 square. What is the potential energy out here? The potential energy out here is given by in the question. See, potential energy is equal to k into r square. So kinetic energy plus k into r1 square. So the total mechanical energy at this point is equals to total mechanical energy at this point. At this point, what is the kinetic energy? Half m v2 square. And what is the potential energy at this point? Half k r2 square plus half, not half, k r2 square. Okay, I have to use this formula for potential energy. Just to explain the situation, I have used the concept of gravitation. But out here, the forces are not gravitational forces. The forces are central forces. That means they behave same type as gravitational forces. Okay. Now what do I need to find out from this equation? A mass. So if I want to find out the mass, just bring this value out here. Bring this kr1 square to the right. So it is nothing but or half m v1 square minus half m v2 square is equals to k r2 square minus k r1 square, isn't it? If I isolate the value of m in the left hand side and isolate the value of k in the right hand side, what do I get? I get half m v1 square minus v2 square is equals to k into r2 square minus r1 square. Okay. Now if I have to find out the value of m, no? So just let us isolate the value of m. So m is equals to k into r2 square minus r1 square divided by 2k v1 square minus v2 square. So this is the value of mass of Earth as given in the question. But there is a little bit of twist out here. Twist is that in the question, okay, see, only the variables of r1 and v2 is given. See, only the variables of r1 and v2 is given. That means in this equation, okay, only the variables of r1 and v2 is allowed. R1 and v2 is allowed. The remaining variable, k is also allowed because u is equals to k r square. Okay, so you have to eliminate the variables of what? V1 and R2, isn't it? V1 and R2 should be eliminated from this equation. And how to eliminate V1 and R2 from this equation? We have to use the equation of conservation of angular momentum. So these are the two equations that I got. Okay, this is the answer that I got. And from this answer, to remove the value of V1 and R2, I have to use this equation. So let's take this two equation on the next page. Okay, I'll just take this equation. Okay, and this equation on the next page, and let's solve them out. Let's eliminate the unnecessary part. Okay, so this is the answer that I got, and I have to eliminate the variables of how much? V1 and R2. So V1 and R2 is not needed. Now from this equation, what you have to do is, this is the answer that we got, and from this equation, I have to eliminate V1 and R2. So from this answer, I have to eliminate V1 and R2. Okay, this is not needed in the answer. Fair and fine. And how do I do that? See, from this equation, can I say V1 is equals to R2 V2 by R1? So V1 is equals to R2 V2 by R1. And can I substitute this V1 out here? So if I substitute that V1 out here, I'll get 2k R2 square minus R1 square divided by, what is the value of V1? The value of V1 is nothing but R2 V2 by R1. So V1 square becomes nothing but R2 square V2 square by R1 square minus V2 whole square, isn't it? Okay. Now if I take V2 common from the denominator, what do I get? I'll get something like AM is equals to 2k R2 square minus R1 square divided by R2 square by R1 square minus 1 into V2 square, isn't it? Now if I take the LCM out here, R2 square by R1 square, if I take LCM out here, what do I get? I'll get nothing but, if I take R1 square as LCM, I'll get R2 square minus R1 square, isn't it? So this much parameter can be replaced by this much, isn't it? So I'll just replace this one, or R2 square minus R1 square divided by R1 square, isn't it? Fair and fine. Now, can I cancel this R2 square minus R1 square from the numerator and denominator? Of course I can. Okay. And after cancelling it out, what do I get? Can I send this R1 square to the top? So if I do that, I'll get something like AM is equals to 2k R1 square divided by V2 square. So this is the mass of the object as given in the question. Okay. Just pause and read the question. Okay. So in this question, there is a mass M of it. Okay. And this mass is suspended by an angle theta with the vertical. That means this angle. Okay. This angle is it. Fair and fine. Now, after making an angle theta, what happens is this mass M is given in velocity in this direction. See? Okay. This mass M is given in velocity in this direction. And follow the trajectory. The trajectory is going in this way, no? Okay. So if I give a very less velocity, what will happen? See? If I give a very high velocity, what will happen? Understood? So whenever I give a trajectory, it will follow a circular path in this direction. Fair and fine. Okay. Now the question is asking, okay, what is the minimum velocity that I must give out in this direction? Okay, so that when it reaches in this side, okay, it makes a 90-degree angle with the vertical, but makes a parallel angle with the horizontal. Okay, I must give a sufficiently minimum velocity such that when it reaches out here, it makes a 90-degree angle with the vertical, or it makes an angle with the horizontal, or it makes 0-degree angle with the horizontal. Okay, see, if I give very less velocity, see, very less velocity, the particle becomes, or the path becomes like this. If I give a very high velocity, see, the path becomes somewhat like this. So at certain velocity, or at certain velocity, what will happen is the path will become like this. Okay, a circular path in this direction. Understood? So let's draw the path. Okay. So this is our wall. This is our ball suspended by an angle theta of mass m. This angle is theta. And when it was released, or when it was given in velocity in this direction, or direction towards the board, what happened? It flew in this angle, making a circular path. Okay. Although this path looks elliptical, but if you see from this side, okay, if you see it vertically from the plane of the circle, It will be a circular path. Understood? So this is a circular path, just not in 2D plane. Okay, this circle is not in 2D plane. That means this circle is not in this plane. Okay, it's a 3D circle, but nonetheless, this is a circular path. Okay, so the question is asking when the ball reaches out here. Okay, what is the velocity that must be given out here so that when it reaches out here, it makes a 90-degree angle with the vertical. Okay, so let's take two positions. The first position is this one, and the second position is this one. Okay, when the ball reaches out here, this is the second position. Fair and fine. I took my two positions. Okay. Now, if I intend to apply work energy theorem, can you tell me what are the total forces acting on this ball? There are only two forces. First one is mg or gravity. Second one is tension, isn't it? Now, if you observe properly, okay, the work done by tension force is always zero. Why? Because string is always tight of fixed length. Okay, so no elongation or compression along the length of string occurs. So therefore, there is no movement along the string. Okay, and tension force always acts along the string, isn't it? So if any movement is to occur, it will always happen perpendicular to the string. Okay, see the length of the string is fixed. Okay, and at every point in the path of the circuit, the string is always tight. That means what? No component of velocity is along the string or is along the string, either compressing it or elongating it, isn't it? That means velocity is always perpendicular to the string, isn't it? That means what? The direction of movement is always perpendicular to the string, and tension force is always along the string. So the direction between displacement and tension will always be zero. So work done by tension force is always zero in this case. Okay. So if I consider a velocity v1 out here, okay, velocity v1 and a velocity of v2 out here. That means when it reaches out here, the velocity is v2. And when I apply work energy theorem, that means final kinetic energy minus initial kinetic energy is equals to work done by all the force on the body, isn't it? So half m v2 square minus half m v1 square is equals to how much? What is the work done by tension force? The work done by tension force is equals to 0 plus what is the work done by gravity force? See, if the length of the string is L or given in the question as L, what is the work done by gravity force? The work done by gravity force is nothing but mg into height, isn't it? And the height is nothing but L cos theta. So this much is nothing but the height. Okay. And the work done by gravity force is negative because mg is acting in downward direction, displacement is happening in upward direction. Okay. So work done by gravity force is nothing but mg L cos theta. Okay. This is the height. What is equals to minus mg L cos theta. Fair and fine. Let's cancel out the m. Okay. So from our first equation, we get v2 square minus v1 square is equals to minus 2gl cos theta. Okay. I just multiply the 2. Okay. I just took half common and multiply the 2 on the right hand side. Then if I multiply both sides by minus 1, what will I get? v1 square minus v2 square is equals to 2gl cos theta. Or v1 square minus v2 square is equals to 2gl cos theta. Fair and fine. Now I got v1 square minus v2 square. I got an equation between v1 and v2. Problem is I must only find out v1. So I need one more equation. And from where do I get that equation? See, it will come from rotational mechanics. Okay. Now observe carefully. Okay. Suppose if I put my observer out here, okay, at this point, my observer is out here. Okay, that means what? This is the origin. Fair and fine. Okay. What is the direction of mg force? The direction of mg force will always be downward, isn't it? Doesn't matter in which part of the circular orbit it is, the direction of mg, okay, will always be downward, isn't it? Fair and fine. Okay. See, now just due to mg, okay, just due to mg, the net torque act or net component of torque in downward direction or any component of torque in downward direction due to mg will always be zero. So what is that? Okay, see, there are two forces acting out here. First one is tension, second one is mg. Okay, the torque due to tension force will always be zero. Why? Because tension is always parallel to r vector. Torque is equals to r cross f. No, so angle between r and f for tension force will always be zero. Okay, so torque developed due to tension force is always zero. Now let's check for mg. Okay, in mg, let me write down the formula. Torque is equals to r cross f. Okay, r cross f. That means first vector, second, this is my right hand. Okay, just because the screen is red, you might get confused, but this is my right hand. Okay, first vector, second vector, resultant vector. Okay, first vector, that means r vector, f vector, fourth vector. Just remember R F, sorry, R F torque. Okay, R vector, force vector, torque vector. Okay, so my force is always downward. Okay, so my force is always downward. Doesn't matter what the value of R is. Okay, doesn't matter what the value of R is. There is no component of torque in this direction. Okay, so what about in this direction? R is in this direction. See, when R is in this direction, there will be two component. Okay, L cos theta, sorry, L sin theta is this much. Okay, and L cos theta. Torque due to L cos theta, mg into L cos theta, torque due to that portion would be zero, no? Because the angle between L cos theta and mg is zero. There will be only component due to L sin theta, isn't it? Okay, so doesn't matter in whichever portion is the ball or in whichever portion is the mass in this circular orbit, torque in downward direction is always zero. Okay, torque due to mg in downward direction is always zero. Tension force in anywhere is always zero. Torque due to tension force in anywhere is always zero, isn't it? So the net torque in downward direction is equals to zero. Now this thing you must understand it clearly. Okay, net torque in downward direction is zero. So net torque in downward direction is always zero throughout its entire orbit. Understood? See, R, F, torque. Okay. Now, if F is always downward, there is no component of torque. This was torque, no? There is no component of torque, okay, in downward direction. The component of torque will always be in this plane. If mg is downward, torque will always remain along this plane or anywhere in the direction of this plane. There will be no component of torque in downward direction. So, throughout its entire orbit, okay, torque will, or the downward component of torque, not net torque, the downward component of torque will always be zero. Okay, let's check out it. Okay, at this position or this position, let's take this position. So what about this position? See, in this position, mg is downward, isn't it? R is in this position. Okay, this is R vector. Now what did I teach? Draw a perpendicular to mg vector or R vector and take the component of second vector along this perpendicular line. So if I draw this one, okay, and this angle is theta. So this is nothing but r sin theta, isn't it? If this is mg, okay, if this is mg, this is nothing but r sin theta. Okay, this is r sin theta. Now r cross f is nothing but mg r sin theta. Understood? And the direction of torque would be nothing but r cross f, sorry, r cross f in this direction or towards zero. Okay, there is no component of torque in downward direction. And what about, sir, if you take the component in this direction? The component of torque in C, if you take r cos theta into mg is nothing but zero. Why? Because the angle between r cos theta and mg is always already zero, isn't it? Okay, so doesn't matter wherever in the part of orbit you are, the downward component of torque is always zero. Now just analyze this situation, okay, because our entire thing is dependent upon your understanding of this fact that the downward component of torque is always zero. Okay, now when you have understood that, then understood a simple thing. Okay, if x component of force is equal to zero, will there be any component of acceleration in x component? No. Similarly, if downward component of torque is always zero, will be there any angular acceleration in downward component? No. So if there is no downward component of angular acceleration, can I say that the downward component of angular velocity will always remain same? Obviously, downward component of angular velocity will always remain same. Okay. Okay, I just made a little bit of thing. Let's not go with angular velocity. Okay. Suppose I say there is no component of force in this direction. I say no, there is no component of force in x direction. Okay. Can I say there is no change in momentum in x direction? Okay. Similarly, if there is no component of torque in downward direction, there is no component of, or there is no change in angular momentum in downward direction, isn't it? So the component of angular momentum in downward direction will always remain constant, isn't it? See, suppose the x component of force is equal to zero. That means what? There is no acceleration, or there is no, not acceleration, do not go through acceleration right now. There is no change in momentum in x direction if there is no force in x direction. Similarly, if there is no change, or if there is no torque in this direction, there is no component of or change of angular momentum in this direction. That means what? If there is no change of angular momentum in this direction, that means the component of angular momentum in this direction is always constant. Okay, that means the component of angular momentum in downward direction is always constant, is always constant. Okay, now this we have understood. Okay, the component of angular momentum in downward direction is always constant. Now, what was the formula for angular momentum? Angular momentum is nothing but m into r cross v. Okay, now see, what is the downward component of angular momentum at position 1? Okay, so if I want my downward component of angular momentum, that means what? R vector, v vector. See the second equation. For the second equation, I'm using my right hand. First vector, second vector, resultant vector. Okay, first vector, second vector, resultant vector. So R is the first vector, v is the second vector, middle finger is the angular momentum vector. That means what is downward component of angular momentum at position 1? Okay, velocity is in this direction. Okay, momentum, or I'm trying to figure out angular momentum in downward direction. So this angular momentum will be downward direction. V1 is towards it, or V1 is in this direction. So what is the component of R? So I must take this component of R, isn't it? So what is this component of R? This component of R is nothing but R sine theta, isn't it? So at position 1, at point 1, okay, downward component, or let's take the downward component of, or downward component as Ly. Okay, Ly. Why Ly? See, if the net velocity is 0, x component is written as Vx, y component is written as Vy, z component is written as Vz. Similarly, if the total angular momentum is L, okay, y component of angular momentum is written as Ly. Understood? So Ly is equals to mass into, what is the component of R that you must take? R sine theta, isn't it? So Ly is equals to R, m into R sine theta. M into R sine theta into what is the velocity V1? Velocity is V1. Okay. Similarly, at point 2, downward component of angular momentum. That means what is the downward component of angular momentum at point? Okay. Okay. At this point, V2 is in this direction. So RVL. So if I'm figuring out downward component of angular momentum, can I say V is in this direction? See, RVL. Okay, L is always downward and V is in this direction. Okay, so I must take this component of R. Okay, and this component of R is nothing but L, because this string will only go and come out here. No, so this much is nothing but L, or the length of the string. Okay, so M into R into V2. And what did I say? The downward component of angular momentum will always remain constant throughout the orbit. So can I say this Ly is equal to this Ly? So this m r sine theta, m L sine theta into V1 is equals to m L V2. Instead of R, I'm writing, instead of L, I'm writing R. Okay, so just change this R with L. L is nothing but the length of the string. So m L into sine theta, m L sine theta into V1 is equals to m L V2. So angular momentum, or downward component of angular momentum at point 1 is equals to downward component of angular momentum at point 2. So from these two equations, I can easily say that ml sine theta v1 is equals to ml v2. Okay, or ml will get cancelled. V2 is equals to v1 sine theta. This is my equation number 2. This is my equation number 1. Okay, now solving equation 1 and equation 2, you get the value of v1, isn't it? So V2 is equals to V1 sin theta. Let's write the two equation on the next page. Okay. V1 square minus V2 square is equals to 2GL cos theta. This V1 square minus V2 square is equals to 2GL cos theta. Okay. This is my equation number 1. Isn't it? And my equation number 2 is nothing but how much? V2 is equals to V1 sin theta. V2 is equals to V1 sin theta. Now this is nothing but just equation solving. Okay. Substitute this V2 out here. Okay. Or we'll get V1 square minus V1 sin theta whole square. I'm just solving the equation. I'm just substituting the value of V2 out here. Okay. Is equals to 2GL cos theta. 2GL cos theta. Or V1 square minus V1 square sin square theta is equals to 2GL cos theta. Isn't it? If I take V1 common, V1 square 1 minus sin square theta. 1 minus sin square theta is equals to 2GL cos theta. Okay. And what is sin square theta plus cos square theta? Sin square theta plus cos square theta is equals to 1. Okay. So cos square theta can be written as 1 minus sin square theta. So this component can be written as cos square theta, isn't it? Because sin square theta plus cos square theta is equals to 1. I'm not writing everything. Okay. Or let me write everything. Sin square theta plus cos square theta is equals to 1. So cos square theta is equals to 1 minus sine square theta. So it's 1 minus sine square theta is equals to cos square theta, 1 minus sine square theta is equals to cos square theta. So v1 square cos square theta is equals to 2gl cos theta. Okay, so cos square theta and cos theta will get cancelled, or v1 square is equals to 2gl by cos theta. Okay, or v1 is equals to under root of 2gl by cos theta. So this is our answer. Okay, understood this question? And most of the solution or most of the cases, this solution is written mostly little bit unintuitively. Okay, most of them haven't explained why the component of downward or why the angular momentum in downward direction is equal to 0. Okay, so the simple concept out here is because the net component in downward direction is equal to 0. That's why there is no change of angular momentum in downward direction. Okay, now just pause and read the question. Okay, in this question, there is a table out here. Okay, and there is a hole in the table. There is a mass tied by a rope, and that rope is put through the hole. Okay. Now suppose I keep my finger out here or keep my hand out here and hold the rope constant. Okay. That means the length of the rope is constant, and give a velocity to mass m in this direction, or give a velocity to mass m in tangential direction. What would happen? The mass m would keep moving in a circular orbit, isn't it? So mass m is keeping moving in a circular orbit. So now what is happening is when the mass m was moving in a circular orbit, I kept pulling the string down with constant velocity v. Okay? So this constant velocity v. So when I pull the string with constant velocity v, the radial direction of velocity of mass m would also be v, isn't it? By constant motion. And whenever there is any kind of circular motion, it is always wise to keep the component along tangential and radial direction instead of x and y. Why? Because x and y direction would keep on changing, no? But the radial or some kind of pattern would be observed in radial and tangential component. Fair and fine. So a body is moving in a spiral orbit, okay, and the radial component of velocity is v. What the question out here is asking is find the total tension in the string. Okay, so what is the total acceleration of this mass m? The total acceleration of this mass m, or the total force on this mass m, is being provided by the tension force. No, is there any other force? Obviously, there is normal and mg force, but those components are in this direction, no? And there is no movement in this direction up or down. So I'm not concerned about normal force or mg force. Okay, so the total acceleration of this mass m is being caused by the tension force by the string, because that is the only force that is connected to the mass m. Okay, so I can write tension force is equals to total acceleration or total force applied on mass m. And what is the total force applied on mass m? Okay, suppose the body was constant, or if the rope was constant, if the length of the rope was constant, if this mass m is moving in a circular orbit, what kind of acceleration is that called? Centripetal acceleration, isn't it? So tension force is equals to centripetal acceleration. Fair and fine. Now, apart from centripetal acceleration, are there any other acceleration in radial direction? No. See, if centripetal acceleration is taken care of, this mass m is moving with constant velocity v. No? So if the velocity is constant, there is no acceleration or there is no radial component of acceleration, isn't it? Apart from centripetal acceleration, if instead of velocity v, if there was an acceleration a in downward direction, so total tension force would be centripetal acceleration plus that radial component of acceleration. But since this tension force or since this string is moving with constant velocity v, there is only one acceleration, and that is centripetal acceleration. And what is the formula for centripetal acceleration? M omega square r. Okay, so tension force is equal to m omega square r. So out here our problem is solved. There's a little bit of problem out here. The problem is the value of r, okay, will keep on varying as the body moves closer to the hole in the spiral orbit. See, r is out here, the r will become smaller out here, r will become much smaller out here, r will become very small out here. So what is happening out here? The value of r is changing. Okay, so there must be relation between omega and r. Okay, why? Because the force, okay, out here is equal to m omega square r. So what is the relation between omega and r? See, one more thing you need to observe out here. Okay, if I put my observer at the hole, okay, my observer is out here at the hole. Fair and fine. If my observer is out at the hole, okay, observing from out here, what is the net torque on this mass m? The total torque on this mass m is being caused by tension force. See, I'm not worried about the normal force or mg force. Okay, normal force and mg force, there is no component of acceleration in this direction. So I'm not analyzing the forces in normal direction or vertical component of forces. Okay, just worry about the tension force. What is the total or what is the torque caused by the tension force? the torque caused by the tension force is always zero. Why? If I apply the formula for torque, torque is equals to R cross F. Okay, torque is equals to R cross F, and this F is nothing but the centripetal force that is caused by the tension. Okay, so the angle between R and F throughout this entire path will always be 180 degree. See out here, F is in this direction, R is in this direction. Out here, F would be in this direction, R would be in this direction. Out here, F would be in this direction, R would be in this direction. So the angle between R and F is always 180, and sine of 180 is always 0. So the net torque or the torque due to tension force is always 0 throughout this entire orbit or throughout this entire path. Okay, so make a note out here. Torque throughout the path is equals to 0. Torque throughout the path is equals to 0. Okay. So if the torque throughout the path is equals to 0, can I say the angular momentum will not change? The angular momentum is always constant, because torque, the value of force is to change the linear momentum. The value of torque or the work of torque is to change the angular momentum. Okay, so if force is equals to 0, there is no change in linear momentum. If torque is equals to 0, there is no change in angular momentum. And if there is no change in angular momentum, the angular momentum throughout the path will always be constant, isn't it? So the angular momentum throughout the path will always remain constant. Okay, and now what is the formula for angular momentum? Check out it. Not out here, out here. Okay, the value of angular momentum is nothing but R cross P. Okay, there is one more formula for angular momentum. Find out the equivalence. What is the equivalence formula for angular momentum? The equivalence formula for angular momentum is nothing but I into omega. See, linear momentum, what is the formula? M into V. So angular momentum will become I into omega. Why I am using I into omega is because out here, if I use linear momentum is equals to R cross V, the tangential component of velocity is not given. Out here, instead of using tangential component of velocity, they have used omega. Okay, or angular velocity of the block. Okay, if they have used tangential velocity in the question that have used tangential velocity, you can obviously use M is equals to or angular momentum is equals to R cross V or M into R cross V. But since angular momentum is given in terms, or since the tangential velocity, okay, is given in terms of omega, I'll use I into omega. Okay, so angular momentum is equals to I into omega. See, it depends on the question. Okay, out here, since in the question omega is used, I'll use I into omega. In the question where tangential velocity is given, I'll use M into R cross V. Okay, so this component of angular momentum or L will always remain same throughout the entire spiral orbit. So can I say angular momentum at this point would be equals to angular momentum at this point? So let's check 2 points. Okay, initial and final. Let's check the angular momentum out here. Okay, and the angular momentum when the block is out here. Okay, the angular momentum when the block is out here. Let this be point 1, let this be point 2, or any other point. Okay, instead of point 2, it should be any other point throughout the orbit. Okay, angular momentum is always constant. Okay, so can I say I1 or moment of inertia of this mass M at this point into angular velocity at this point is equals to moment of inertia at any other point? That means if you are finding out the angular velocity out here, that you have to calculate the moment of inertia out here. So moment of inertia at point 2 or any other point into angular velocity at that point. That means if I am calculating the angular velocity omega or some other value out here, I have to calculate the moment of inertia out here. Fair and fine. And what is moment of inertia of a mass M, point mass? M into R square. So M into R square or R1 square omega 1 is equals to mass into radius at which I'm finding out the angular momentum. Okay, M R square. You can find it out here also, you can find it out here also. That means point 2 can be located out here also, out here also, out here also, out here also. Okay, this is nothing but point 2. This is nothing but point 2. Okay, this equation is of point 2. Okay, M into R2 square. Okay, and this omega. Omega is nothing but angular velocity out here. Okay, this omega 1 is nothing but angular velocity out here. Okay, angular velocity out here. This angular velocity is nothing but the angular velocity out here, or any other point at which you are calculating the angular momentum, isn't it? Okay, now in the question it is given initially when the value of R was equals to R naught. Okay, the value of angular velocity is equals to omega naught. So let's say initially when the value of r1 is equals to r naught, the value of omega 1 was equals to omega naught. So initially instead of using 1 and 1, I'll use when the value of r was equals to I naught omega naught, the value of r was r naught and the value of omega was omega naught. Okay. So from this equation, if I take this two equation, can I say m r naught square omega naught square? Sorry, m r naught square omega is equals to m r square omega, isn't it? So if I take this two equation, m r naught square omega naught is equals to m r square omega. Cancel out the m. Okay. So from this two equation, I can get r naught square omega is equals to r square omega. Okay. Now see, using this simple relation of torque, can I say or can I substitute this equation out here? Isn't it? That means as the body throughout the entire portion of the spiral orbit, I know that at what value of r will become what value of omega. See, if the initial condition is given, that means these two values are known. Now you just have to plug in r, the value of omega will be out. If you plug in the value of omega, the value of r will be out. Because these two are already given in the question. That means this is known out here. Okay. So if I plug in the value of r square omega out here, what do I get? Let's check. Okay. Substitute anyone. Okay, let's substitute let's say omega. I'm going to substitute omega out here. Okay. T is equals to m r, or I'm going to substitute what am I going to substitute? I'm going to substitute r square. Okay. I'm going to substitute r out here. So r out here is nothing but r naught square omega naught by omega is equals to r square. Or let's do the opposite. Let's substitute omega because there will be a component of under root. I don't want under root in my equations. Or r naught square omega naught by r square is equals to omega. Okay. From this equation, I'll just substitute r naught square or r square down out here. Okay. So if you put r square down out here, it will be r naught square omega naught by r square is equals to omega. Now just substitute this omega out here. Okay, in this equation. So m omega square. What is omega square? Omega square is nothing but r naught square omega naught by r square whole square into r. Okay, m omega square r. So the value of tension force will be nothing but m into r naught to the power 4 omega naught square, then r divided by r to the power 4. If I cancel out this r and this r to the power 4, it will become r to the power cube in the denominator. So this value becomes nothing but r cube in the denominator. Okay. So this out here is the answer for the tension force throughout the spiral orbit. That means what? The tension force throughout the spiral orbit keeps on changing. Okay. As the body moves towards the center of the hole, the tension force becomes greater and greater. See, if you move this body or as the spiral orbit becomes closer to the hole, the value of r becomes very less. When the value of r becomes less, what is happening? Out here, the numerator is already a constant, isn't it? Every component of numerator, m into r naught to the power 4 into what is it? Into omega naught square. Into omega naught square. This is nothing but omega naught square. The numerator is already a constant. Okay. So as the value of r is decreasing, the value of tension force is increasing. Okay. So as the body moves closer to the hole, the value of tension force keeps on increasing. So you plug in the value of r, okay, you find out the value of tension force. The tension force at this r is equal to this value. The tension force at this r is equal to this value. See, the tension force will be variable. Okay. And the tension force is given by this value. The main concept of this question was the only acceleration faced by n was centripetal acceleration. Okay. And this centripetal acceleration will keep on changing. Now to find the pattern of this changing centripetal acceleration, I've used the concept that net torque on mass m is equal to 0. So angular momentum of mass m will always remain constant. And the value of tension force will become this one. And this is our answer. Okay.